Hello. Today in this video, I'd like to talk about pH calculations with bases and salts. Similar to what we saw with acids, we're first going to take a look at strong base calculations, then take a look at a bit of a harder subject with weak base calculations, and then finally take a look at how you calculate the pH of different salt solutions. These can be either acids or bases, depending on the salts. To take strong bases first, we know that strong bases, like strong acids, do not exist in equilibrium. Their ionization reactions go to completion. And so, because of that, the concentration of my base in solution is going to be equal to my OH minus concentration. So, for example, we know the strong bases include things like the group 1 metal hydroxides, and one caveat, it also is going to include a few of the group 2 metals, calcium 2+, strontium 2+, and barium 2+ hydroxides as well. We're going to consider those strong bases. So for these strong bases, I can assume the OH minus concentration is related to the base concentration. So to take a look at an example, what is the pH of 0.1 molar NaOH? Well, to do this, I know that 0.1 molar is going to be the concentration of both my NaOH, and because this goes to completion, my OH minus ion. Those are both 0.10 molar. Now I can't quite directly calculate pH from my OH minus concentration, so instead I'm going to have to use pOH first. Say that the pOH is minus the log of the OH minus concentration. So then I'm going to take minus log of 0.10 molar, and from that I'm going to get that to be 1. From there, I know that my pOH is related to pH using the equation pH plus pOH equals 14. Plugging in my pOH as being 1, pH plus 1 equals 14, therefore pH equals 13. And this makes sense. I have a high base concentration because I have, or a pOH, because I have a high base concentration. A strong base should produce a fairly alkaline pH. Now, there's one other tricky thing here, and that's what do we do with bases that have multiple hydroxide ions? Unlike the acids, which have those diprotic and triprotic things where we can consider them multiple equilibria, for these metal salts of hydroxides, like calcium hydroxide, we're going to say that for every calcium hydroxide, I get 2 moles of OH2. Essentially, I'm considering this reaction here, where that splits up into calcium 2+ and 2 moles of OH minus. And so if my molarity of my calcium hydroxide is 0.15 molar, and let's make that into concentration, then my molarity of my OH minus is twice that concentration, and therefore 0.30 moles. And so that's the only tricky thing when we're dealing with these strong bases that have multiple OH minus ions. From there, the calculations will work the same. I then can take that the pOH is minus the log of my hydroxide ion concentration, 0.3 molar, and when I do that, I end up with 0.52. Plugging into my equation, pH plus pOH equals 14. It looks like I end up getting 13.48 as my pH. Again, quite a basic pH because I have a strong base in solution. Now, let's go ahead and take a look at weak bases. Just like we saw with weak acids, weak bases do exist in an equilibrium, and you want to be able to write out this equilibrium reaction, namely that B plus water is in an equilibrium with HB plus and OH minus. And so if I write my Kb expression, my equilibrium constant, Kb will be HB plus times OH minus divided by my base B. Now, in order to solve this, I'm going to have to use our old friend, an ice table. So let's take a look at a specific example. What is the pH of 0.15 molar NH3? Well, if you look in the back of your textbook, we know that the Kb, the base dissociation constant for NH3, is 1.8 times 10 to the minus fifth. Setting up my ice table, I'm going to have my base is NH3, my conjugate acid is NH4+, and then I have OH-. Initially change in equilibrium, I have 0.15 molar of the NH3. I'm going to assume we start with 0 of each of the NH4 and the OH-. This is going to go down by an amount x, up x, up x, and I finally get in my equilibrium concentration 0.15 minus x, x, and x. Now, once again, I can make the small x approximation. 0.15 is more than 2 orders of magnitude away from my 1.8 times 10 to the minus 5th, so I can go ahead and cross out my minus x here and assume that that x is very small. From there, writing my equilibrium expression, Kb is 1.8 times 10 to the minus 5th, which is going to be x squared divided by 0.15. If you run those numbers in your calculator, you should end up getting an x equal to 1.6 times 10 to the minus 3rd molar. Now it's important to remember that this x represents my OH- concentration. I'm looking for pH, so similar to what we saw before, we're going to have to take that extra step here of calculating out my pOH first. So it's going to be minus log of 1.6 times 10 to the minus 3rd. Throw that in your calculator. My pOH I end up getting 2.8 as, and so my pH then is 14 minus that, or 11.2. So as you can see, it's very similar to our weak acid calculations. I just need to remember that I'm calculating OH- first rather than H+ first and plan accordingly. Now let's take a look at salt pH. Now fundamentally, it's actually no different than either of the weak acid or weak base calculations, because salts are always going to be either a weak acid or a weak base. Let's take a look at the example we saw in our last time, which was NaHCO3. And I'm going to find out what the pH of this salt is here. Now, you want to be able to make the prediction that because Na is the conjugate acid of a strong base, it will have no effect on the pH, whereas HCO3 is the conjugate base of a weak acid, and so this salt is going to be weakly basic. I would then need to go ahead and look up the Ka of the conjugate acid in my textbook. The Ka of H2CO3, it looks like, is 4.4 times 10 to the minus 7th. But what I really need is the Kb for my HCO3, because when this dissolves in water, the hydrolysis reaction I'm going to get is HCO3 minus plus water is in equilibrium with H2CO3 plus OH minus. So to find that Kb for my HCO3 minus, I remember that Kw relates my Ka and my Kb. I plug in 4.4 times 10 to the minus 7th for Ka. Kw is 1 times 10 to the minus 14th. And so the Kb I'm going to calculate looks like it ends up being 2.3 times 10 to the minus 8th. Now remember, this relationship only is true for a conjugate acid-base pair. Now that I know my Kb, I can go ahead, finish off my ice table here. I'm starting with 0.50 molar HCO3, 0 of each of these. H2O is a liquid, so it doesn't play a role in my equilibrium. This is then going to go down by some minus x, so 0.50 minus x, plus x, plus x. X and x are my equilibrium concentrations of H2CO3 and OH-. From here, this looks exactly like a weak base equilibrium. Solving this out, 2.3 times 10 to the minus 8th is going to be x squared divided by 0.50 minus x. Luckily for us, we can again make the small x approximation. That x is going to be small. Therefore, I can take 0.5 times my 2.3 times 10 to the minus 8th, take the square root of that number. I get x to be 1.1 times 10 to the minus 4th. And that x then represents my OH- concentration. From there, I need to calculate the POH first, which is the minus log of 1.1 times 10 to the minus 4th, and that ends up being 4.0, and then finally my pH would end up being 10.0. So as you can see, salt calculations just depend on whether we can predict whether it's weakly acidic or weakly basic, finding out the Kb or Ka for the conjugate, and then from there setting up the same ice table we've seen for weak acids and weak bases. Okay, that's been it for base calculations and salts. Thank you so much. I'll see you next time.